Okay, so welcome to the first actual content lecture of Physics 137. Physics 136 was mostly a foundational physics course. Although we studied some pretty cool things in Physics 136, mainly the crown achievement being angular momentum and gyroscopes. I think those are absolutely amazing and absolutely blow my mind. By far my favorite topic is angular momentum and gyroscopes. I would say overall, Physics 136 was quite boring. And although I love physics, and every time I drive, every time I walk, I just see physics everywhere, I'm fully willing to admit that the material in 136 is a little bit dry and a little bit boring, because it's very foundational. You know, we had to pioneer the laws of motion. We had to pioneer conservation of energy and very fundamentally conservation of momentum. It was all the heavy lifting and all the grunt work that was very fundamental and quite dry. This class, Physics 137, we focus on quote unquote modern physics. And when I say modern physics, I mean physics from like 1910 onwards. When we did Physics 136, that was like 200-300 years old physics. So not 1910, right? 1910 was only about 100 years ago, maybe 110 years ago. In fact, I mean, a lot of your grandparents, if they're still alive, well, actually, I don't know. If my grandmother was still alive, she would have been born in, I think, 1905. So the physics we're going to learn in this class is so, well, not so new. 100 years isn't so new, but it's new enough that you probably would have been alive to know somebody that was alive during a time that this physics didn't exist. And I just think that is just fascinating, that we are learning things now in a first year class that we just accept in mainstream knowledge to be fact, that just was a completely new concept even 100 years ago. To me, that's just fascinating. And I think students kind of pick up on this inherent fascination. And course feedback historically is that Physics 137 is more fun and more interesting. And although it's harder, because the material is harder, students historically tend to have more fun with Physics 137 because it's less dry. So anyway, that's my sort of preamble to the class. Just a sort of big picture to how this class is going to unwrap for you. This whole class, we are going to be studying forces at a distance. Whereas with Physics 136, it was primarily contact forces. Things like tension, things like friction, things like the applied force where you push or you pull on something. Or Newton's third law, for every force there's an equal and opposite reaction force. If we push on a block, the block pushes back. Or the force during a collision when two things are physically colliding and touching each other. You know, Physics 136 was very, very concrete, so to speak. You can see it, you can feel it, you can explain it. The only non-contact force we studied in Physics 136 was gravity. And what do I mean by non-contact? It's a force that acts on an object through non-contact, right? Gravity is acted on every object, and it can happen at a distance, right? Earth does not need to touch our feet to pull us toward Earth. That's what I mean by non-contact force. Whereas tension, the rope has to be physically attached to the object, contact, in order for the tension in the rope to affect that object. Now, for whatever reason, luckily I guess, students do not historically have an issue understanding gravity. Maybe it's because their brain and their body experience gravity on a day-to-day basis, so it's easier for them to grasp the notion of an invisible force of gravity. However, I will be very upfront. This entire class is talking about forces at a distance. And historically, students have a substantially more difficult time grasping these concepts, even though it's the same sort of virtual forces at a distance, non-contact forces. There's something about the electric force and the magnetic force that just blows people out of the water. Students historically have a hard time wrapping their heads around it. And I've never understood why, because to me, it's the same idea as gravity, Who knows the mechanism by which gravity works, whether it's Einstein's theory of relativity and it's the curvature of space-time, or whether it's the virtual exchange of gravitrons, or gravity particles. I don't know, I'm not a particle physicist, but if you are a particle physicist, you would not believe in theory of relativity. You would think gravity is through a virtual exchange of I think they're called gravitrons, whatever. Anyway, the mechanism by gravity, I don't care about. I can explain it. You know, I can explain its work. I can predict its motion and explain its effects. Same thing with the electric and magnetic field. To this day, physicists do not know the source or the mechanism by which electric forces can act at a distance. We do not know that, but I just accept that and kind of move on. So in my head, this is no different than gravity, but for some reason, students are really fixated on, well, how does that work? Why does that work? I love those questions, how and why, but unfortunately, physics does not yet have an answer to those, so we just kind of have to move past it. So I'm giving you that sort of fair warning now. When you do find yourself kind of questioning how and why, good, embrace it, but don't get hung up on it. We also, in this class, will talk about Maxwell's equations. Those will be Greek to you, no pun intended, presently, but I want to draw the analogy that Maxwell's equations are, they're the governing equations of electricity and magnetism in the same way that F net, conservation of energy, conservation of momentum, etc., are the governing equations for classical physics. You know, F net equals ma governs forces and acceleration. Kinematics equations govern, assuming motion exists, where is it going to go. Conservation of momentum quantifies how much motion something has. You know, those are the governing equations, head honcho equations for classical physics, and Maxwell's equations are the governing head honcho equations for E and M. So that's going to be the storyline. We're going to revisit all of the same talking points that we did with Physics 136, but in the context of Maxwell's equations. Okay, so I do try to do this sometimes, but it's really important we lay out a narrative here, because this is going to set the scene for the whole course. Literally this narrative is going to be the entire class, and we're going to be telling us ourselves this story repeatedly through the whole class. So what are we doing here? We notice that there is a charge. The Greeks, the ancient Greeks noticed this many, many, many eons ago. They noticed that if they rubbed a piece of amber against fur, they noticed they would get little sparks, or they could like affect the fur. The fur could stand up, and you know, if they rubbed the amber, they could get like a little shock. You know, like when you shock your car when you get out of your car or something like that. And we, to this day, we're like, yeah, whatever, we understand electrons and all the other stuff. To the ancient Greeks, that was mind-blowing. Like, you have to understand, like, ancient Greeks, they didn't have any notion of physics or hardly at all science. You know, so to them, they found this absolutely fascinating. That was the first clue that charge existed, was way back in the ancient Greek times. So the narrative we're telling ourselves is, we notice a phenomenon, which is what science is about. We notice a new event, and in this case, the new event would be, we notice sparks or some sort of charge, and now we have to sort of figure out the new realm that we've uncovered, that we've only scratched the surface of. So what is charge? Okay, well, we've also noticed that charges can attract and repel. We notice the amber can make the fur on animals move. You rub a balloon on your hair can move around. So we not only are there charges, we investigate properties of these charges, and we say, oh, look, there's a force associated with these charges. Okay, well, being physicists, our job is, once we notice a new type of force, we have to quantify it. You know, force of gravity, mg, celestial gravity, gmm over r squared. Right? Force of friction, UFN, right? Any type of force we've discovered, we've quantified. So that's what we're doing. We notice there's a new force, we're trying to quantify it. Now, this is going to be gibberish to you. It momentarily will make sense, but the narrative we say is, oh, look, for us to actually quantify this new electric force is actually going to be hard to do directly. And I understand that at the moment that doesn't make any sense to you, We will get to that shortly, but I'm telling you that the plot line, I'm spoiling the book for you. What is it? Like, I'm showing you a movie trailer by showing you the beginning, middle, and end, so to speak. So in order to solve for the formula, we actually have to take a detour and we have to introduce a notion of an electric field. And then we have to lean on Gauss's law. Gauss's law is one of Maxwell's equations. It's one of the governing equations of electricity and magnetism. It's equivalent to sort of, F net equals ma, so to speak. It is a head honcho equation. And then after we do all the heavy lifting in here, then and only then can we conclude with coming up with a formula for the electric force. So by the end of lecture tomorrow, we will be able to finish the last bullet point. That's how long it'll take for us to get there. Okay, so electric charge. Let's go back to the beginning of the story, right? The beginning of the story is we notice there's a charge. We go way back to the ancient Greeks, okay? What is charge? Well, let's not overcomplicate it. I don't want to regurgitate the whole process the Greeks went through to figure all this out. Let's just jump to the point. There are two types of charge, positive charges and negative charges. As we know, probably from elementary school, like charges will repel, right? So a proton and a proton, or a positive and a positive, will repel each other. Similarly, so will a negative and a negative, they will also repel each other. Opposite charges will attract, so positive and negatives attract. Perhaps that's where the romantic saying opposites attract come from. Trust me when I say in practice, in terms of personality, that is not true. You definitely need to have more in common with your significant other than you have not in common. So I don't know, maybe that's just someone making a cute saying out of a physics fact, I don't know. Anyway, the last thing that is maybe not so commonly known is that some neutral objects, some charged objects can attract neutral objects. And I know you've all seen this before. It's just kind of a formality that we're trying to explain. That way it's in your head as something official and not something like, oh yeah, I've always known that. I just never really thought about it. Well, now I'm forcing you to think about it. Okay, here's a conceptual example. I've done a lot of talking. So we have a few of these sort of questions. Depending on time, I might do all of them or I might skip some of them. But it's been about an hour and 20 minutes of, well, no, an hour and 10 minutes of me talking. So not only does my voice need a break, I think you guys might need a little bit of an intermission. So what I'm going to do is I'm going to launch a poll, like a multiple choice poll. And I'm going to have you answer on the poll. So let me just launch that now. You are logged in from I apparently cannot launch a poll. That's unfortunate. I don't know. Hold on. Is that because, I don't know, maybe I was logged in on my phone? I don't know. Let's try this again. Nope. Okay, I don't know. I'm not able to launch the poll. All right, so maybe we won't do this on the poll. I'll figure this out for maybe tomorrow. So we'll just talk about it then. And I don't know why I can't launch a poll. So here, two charged balls are repelling each other. So we know that as a fact because we can observe that fact. As they hang from a ceiling. What can you say about their charges? One is positive and the other is negative. Well, that can't be true because if they were, they would be attracting each other. So that's wrong. Both are positive. Well, that might be true because in the event both spheres are positive, they would be repelling each other. So maybe that's true. C, both are negative. Well, if they were both negative, they would also repel each other, right? Because like charges will repel. So this one's also true. Now, multiple choice questions usually there's only one answer unless otherwise specified. So the fact that we have two right answers probably means the last question is all of the above or some variant on that. So if we read part D, it says both are either positive or both are negative. So we've already concluded that they're either both positive or both negative. So that means D is the correct answer there. So another example is slightly more complicated than what we just did. So from the picture, what can you deduce or conclude about the charges of the balls? So we know green and purple repel each other, and we know green and yellow repel each other. So that's the fact that we know. What can we conclude using this fact? Well, pink and yellow have opposite charges. Well, I don't think so, but we'll come back to that. Pink and yellow have the same charge. All three have the same charge. One must be neutral. Well, you should always be wary of the word must. That's a very strong word. Odds are must is probably not true. Is there a scenario in which one of them could be neutral? Yeah, probably. But the word must, I'm not so sure. So I'm just using psychology. I'm going to cross that one out. Let's see here. The fact that green and purple are repelling each other means whatever charge green has is the same as purple or fuchsia or whatever the hell those called, pink, whatever. This means if this is positive, then this will also be positive. Now, if we assume this was positive, then this green one will be positive as well. Now, green also repels yellow. Now, if they repel, then they're like charges. And if they're like charges, then if green was positive, then yellow will similarly be positive. So that means they're all the same charge. If we went back and said, well, maybe green is negative, well, then that would make pink negative. And then that would make this green negative, because that's what we assumed. And then that would in turn make yellow negative. So they're either all positive or they're all negative, which means the answer has to be all three have the same charge. So there's the answer there. Okay, quantization of charge. Students often they know this fact from high school and chemistry, but they often sort of don't realize that this is sort of a cool sort of feature. Charge is quantized. You know, often we talk about, even in chemistry, you can talk about, you know, how much charge something has. In physics, you can say, yeah, I've got so many coulombs of charge. But it's quantized. The fundamental unit of charge is an electron or a proton. And you can't get anything smaller than that. Now, the charge on an electron, and I'm saying this as if it's common knowledge, the charge on an electron is 1.602 times 10 to the 19 coulombs. Coulombs is the unit we use for charge. Now, where did that number come from? Actually, that was a huge breakthrough in science. The Greeks figured out that electrons existed, but it wasn't until relatively recently that we were able to actually measure the charge of an electron. It was, you may have learned this in chemistry class, or maybe physics, depending kind of how good your high school teachers were. There was a controversial scientist by the name of Millikan's oil drop experiment, as they call it. Millikan was the one who actually predicted the value of the charge of an electron. And he's controversial because he was probably one of the worst scientists in terms of, I mean, he was a good scientist, but he fudged his data, which is a big no-no in science. And the way he fudged his data was if he got a data point that he didn't like, he would just ignore it. And he would only keep the data that he liked. That's not how science usually works, but for some reason he was onto something. He had something in his head and it turns out he was right. Yeah, he was the one who predicted the charge of an electron. So I say this as if it's common knowledge. Historically it wasn't. It was a very big breakthrough when they came out with definitively the charge of an electron. But that means charge is quantized. You can't have a smooth gradation of charge. If you zoom in, it'll look like a step. You either have 1 electron or 2 electrons or 3 electrons or 4 electrons. You can't have 4.5 electrons. That's not how that works. So you can't have a smooth function of charge. Now, that's mathematically. Mathematicians and physicists have a sort of cute animosity for each other, a collegial animosity for each other. We're not actually mean towards each other, we're just playful. Mathematicians, quote unquote, hate physicists because we fudge math all the time. And what physicists say is, okay, well, technically you're right, charge is quantized. Technically, but look at the magnitude here. It's 10 to the minus 19. How many digits do your calculator have? Like 9, 10 at most? You know, I don't even think my calculator has 9 digits. You know, and when we write numbers down, do we even keep anything past like the second decimal place usually? No. This has 19 decimal places. Are you kidding me? 19. So physicists, we're just like, okay, screw it. The step is so shallow that it effectively appears smooth. So in physics, we pretend charge is not, well, we acknowledge it's quantized, but we never talk about it being a discrete function. You know, we never worry about saying, well, you know, are we getting an answer of 1.5 electrons? We don't really care about that because the 19th decimal place is such a small number. We don't have instruments that even are precise enough to measure that. We barely have instruments that are precise enough to measure 2 decimal places, let alone 19. So in physics, you know, we acknowledge, it is true that the total charge on an object, Q, for that silent Q in charge, I don't even know why physicists decided to use Q for charge, probably something Latin based or whatever, but anyway, we acknowledge that the total charge is an even, a whole number multiple of the electron. We acknowledge that, but I'm not going to dwell on the fact that it's quantized. There's not going to be any like technicalities. Oh, technically you're wrong because it's quantized. No. We pretend it's smooth because mathematicians can go hide in the corner because that's where they like to be. So if any of you are like really into math and want to challenge me on that, I will tell you to go hide in the corner. Okay, moving right along. So I alluded to this earlier, how charged objects can sometimes attract neutral objects. And you've all seen this in your everyday lives. I mean, styrofoam, you know, like the clinginess of styrofoam, like that's an example of what I'm about to talk about. But I can understand a lot of you are not from a physics background. You are perhaps from a bio or a chemistry background. So maybe this example is more conducive for you guys. The notion of polarization in molecules. This is what I'm talking about. So if you have something that is polar, like for instance, water is neutral, might I add, right? It's H2O nothing. It's not like +1 or -1, it's just H2O. It's a neutral molecule, but it's polarized. And what does polarized mean? It means that one side of the molecule is more positive than the other side. So in this case, this is the positive end, right? This is where the protons are, or the hydrogen nucleus, which is just an H, or just a proton. And then this side, you've got 2 lone pairs. So this is the negative side. So water is polarized. And how does this attract an object? Well, it induces a dipole. And because this side is more negative, what it does is all the evenly distributed electrons, let's say hypothetically on this xenon atom, it would actually repel all of the electrons to one side, and thus leaving this side negative and this side positive. And then this is where we have the instance where like charges repel and opposite charges attract. You've got negative and positive, so they're going to attract. So that's for instance, an example of how neutral objects can be affected by charged objects, and actually how neutral objects can be affected by fellow neutral objects, which is kind of really cool. So the answer to that is polarization. How do you manipulate neutrally charged objects? The answer to that is through polarization. Common, like outside of chemistry, for instance, macroscopically, things that you would have experienced to be polarized are things like styrofoam is a very common thing that is polarized. Clothing, you know, when you take things out of the dryer, you get the static socks that stick to everything. You know, those things that are only charged because they can be polarized, stuff like that. Okay, so here's an example. I would launch a poll, but apparently for some reason I'm not able to do that. So we're just going to talk about this. A metal ball hangs from the ceiling by an insulating thread. The purpose of mentioning the word insulating thread is because charge is then not able to flow through the cord. We will talk more about insulators and conductors momentarily, but for now, just roll with it. The ball is attracted to a known positive object. So we know this is positive. And we can see empirically that the ball attracts to it. The charge of the ball must then be, well, opposites attract, so that means negative. Right, so that's fairly, oh, sorry, I jumped the gun on that one. Again, must, I jumped the gun. You have to be careful with the word must. Must. So, does it have to be negative? No. Could it be negative? Yes. I jumped the gun on that. I didn't read the word must, my apologies. So this is one possibility. Could it also potentially be neutral? Yes, as we've just discussed, right? These positive charges in this rod would attract, I'm gonna draw this in blue because everyone knows electrons are blue. Joking, of course, electrons don't have color. It would attract the electrons and that would leave the other side positive. And of course, everyone knows protons are red, which is of course hilarious because that's also not true, but it's just in every friggin' textbook, electrons are always written to be in blue and protons are always written to be in red. I don't know why, but anyway. So you could have a neutral object that's being polarized and then thus attracted. So the answer is either neutral or negative. So that would be E, neutral or negative. Okay, so where does that leave us? Well, I mentioned I'm having Zoom problems or zooming problems. There we go. So I mentioned in the previous question there was an insulating wire, and we hadn't yet talked about insulators and conductors. So let's do that now. Let's clear the air. We have this notion in everyday English. You don't need to take a physics class to be familiar with this idea. We have the notion of what is a conductor and what is an insulator. And through our everyday experiences, we mostly see that metal is usually classified as a conductor. Now, you may not know the physics of why, but it should be fairly easy for you to kind of jump on that bandwagon that metal is a conductor. And you also have a certain notion of what's not a conductor or insulator. Again, without any formal physics training, that's not so hard to figure out. Would I say wood is a conductor? No. I think we can all agree that wood would not be a conductor. Here's the technicality. And this is hilarious, actually, because the technicality is not much more clear than what you're used to not in a physics class. You would expect that because this is a science, everything's rigid and everything has a technical definition. Funnily enough, there isn't really a good definition of conductor and insulator. The best definition, without overcomplicating anything, is a conductor is considered something that easily, quote unquote, easily allows for the flow of charge. Okay, cool. It's not a very technical definition. I agree with you. It's just, it is what it is. I'm just presenting the facts as they are. What is an insulator? Materials that don't allow for the easy flow of charge. It's as simple as that. There's really no need to overcomplicate it. So you might be asking yourself, okay, Mark, that's fine and dandy, but how do we know what's defined to be easy and what's defined not to be easy? Well, that's a great question. I would just say use your experience as a human being. You know, if you used wood as a wire, is it going to work well as a conducting wire? Probably not. You know, there's a reason why we don't make wood wires. It doesn't really conduct electricity very well. There's a reason why we use metal wires or copper wires, because they do. So define easy, just use your day-to-day experience of what a conductor is. Now, I can help you a little bit with quantifying, like assigning a number, not 1 to 10, but nonetheless a number of what's easy or of what's conductive and what's not. Each material that exists in life concrete, wood, air, water, salt water, copper, aluminum, anything, any piece of string, cotton, right? Any material will have an innate ability to conduct some form of electricity. We call this number, or this ability, we call this the conductivity of the material. Now, as we've already imagined, some things have more ability to conduct than others, which means metal will have a higher value of conductivity, a higher sigma value. And things that are traditionally viewed to be insulators, like wood or air or rubber or plastic, they will have a lower conductivity or a lower sigma value. So it's like a spectrum, I guess is what I'm saying. Everything is conductive, sort of, and the more conductive something is, the larger the sigma value, and the less conductive something is, the smaller the sigma value. Now, it's really annoying talking about small numbers, like 10 to the minus 19 or whatever, blah, 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 like charge. So when something is considered to be an insulator, instead of saying, oh, its sigma value is times 10 to the minus 20, we just talk about the opposite. If something's known to be classically an insulator, we can talk about the resistivity of the material. And the resistivity of the material is defined to be the inverse. So we know sigma will be equal to 1 over rho. So they're just literally 1 over each other. They're in literal inverses of each other. And this is only because humans have a tendency to not like small numbers. It's harder for us to say 0 point blah, blah, blah times 10 to the minus 3. It's easier for us to just say 2,000 or something like that, because the inverse of 10 to the minus 3 would be thousands. So when we are talking about material that is known to be an insulator, we typically talk about the resistivity of the material, typically. Now, let me just further illustrate what I'm trying to say with the previous slide, that everything is a spectrum, okay? Conductors, technically everything's a conductor. Some things just conduct better than others. Here's what I mean by that. I think we would all agree that air, for instance, is classically defined to be an insulator. Proof of this is wall sockets are just exposed to the air. And hopefully you've never done this, but I mean, you see videos of this every now and then online. You get some child that puts a fork or a knife in a wall socket. Maybe they're just being good scientists and they're exploring, I don't know. But you put a knife in a wall socket and they get electrocuted and shot across the room. That's because the knife is metal and a conductor. So, the electricity travels through the knife into their body and then bad things happen. However, air is touching the wires in the wall socket and we're not being zapped with electricity. In fact, I can even place my hand directly on a wall socket and still not get shocked because there's still that sort of air gap between the wires and my hand. So classically, I think we can all agree air is an insulator. It does not readily allow for the flow of electricity very easily. However, what is lightning? All lightning is a bolt of electricity that connects the circuit between the air or the clouds and the ground. So when you have lightning, you have electricity that is traveling through air. In the event of lightning, air is acting like a conductor. So this is a very common example that we've all experienced, and if you've never experienced lightning, you are missing out. I think lightning is the most fascinating thing on this planet. It's a naturally occurring phenomenon and it has such power and such complicated physics implications. I just think it's so amazing that it happens naturally. Anyway, we won't get into that. This is an example that you can see with your own eyes, that you have an insulator that sometimes acts as a conductor. So this illustrates that there are no such things as insulators or conductors. There's a spectrum. Even why are wires in houses copper and not steel or nickel or aluminum, right? Even of the metals, there are different metals that conduct electricity better than other metals. Copper just happens to be a type of metal that conducts very easily compared to other metals. It has a higher sigma value compared to other metals. That's why copper wiring is used. We could use aluminum wiring, but we would be wasting more energy because it has a lower sigma. So we would lose more energy in heat and resistance that way. So, you know, it's a spectrum. Now, I want to define it, before moving on, I want to define a term, something called breakdown voltage. We haven't talked about voltage yet. We will, maybe give it till Wednesday. Without going into the definition of voltage, I want to talk about breakdown voltage. What that refers to is the voltage at which you can force electricity through a particular object. What that effectively says is that everything is a conductor if you push hard enough. What is the breakdown voltage of metal? Close to zero. A very small amount of push will get electrons to very easily flow through metal. What is the breakdown voltage of wood? Very high. You need a large push to push electrons through wood. Electrons do not want to go through wood, but if you push hard enough, they will. Same thing with air. Electrons do not want to go through air, but if you push hard enough, they will. That is the idea of breakdown voltage. Every object has breakdown voltage. It's just, you know the phrase, everyone has their price? Oh yeah, you know, I like that necklace you have. Just sell it to me. Oh no, the necklace isn't for sale. Well, everyone has their price. If I offer you $1 million for the dollar store necklace, you're gonna sell me the necklace. Everyone has their price. Same thing here. Every object has a breakdown voltage. Name your price. Everyone has a price. Every object has a breakdown voltage. There will be a point when every single object known to man will allow electricity to pass through it. The question is, are humans able to generate enough push to get it through there? So like rocks, for instance, I don't think we're able to generate a voltage man-made high enough to get it to go through rocks. But in theory, it's possible. Maybe lightning. I mean, nature has a tremendous ability of generating high voltages. So maybe nature can get something to go through a rock, but you know, that's what I'm trying to say. That's a for instance. Okay, we already talked about that slide. Okay, so moral of the story, takeaway here, I've said this enough times. Keep it simple. Conductors will allow charge to flow, insulators don't. Okay, so now let's talk about the flow of charges. Let's talk about insulators and conductors in the context of having them flow. So you've got two neutral conductors. Neutral conductors are connected by a wire and a charged rod. So they're neutral conductors and they're connected together by a wire. And you bring close a charged rod. So the rod has, let's say, positive charges on it. But it does not touch any of the objects. Action at a distance. I mentioned that earlier, action at a distance. The wire is then removed. See here, we see there's no wire. The wire is then removed. What remains or what becomes of these objects? So let's think about what happens. Let me erase my doodles here. When you have this charged rod that comes, you're going to be repelling like charges and attracting opposite charges. So you're going to be repelling all the positive charges and you're going to be attracting all the negative charges. Now, if I were to remove the positive rod away and that yellow wire stayed put, then there's nothing separating these charges anymore, and then the charges would mix together and intermingle and everything would go back to normal. However, while the rod is still in and around the vicinity, we remove the wire while the charges are still separated. If we remove the wire while the charges are still separated, then we still have negative charges on the blue object and positive charges on the green object. And after we remove the connecting wire, we take this away. The objects want to go back to where they used to be. They want to go back to being neutral, but they're not able to, because air is an insulator and does not readily allow for the flow of charges. So the electrons would want to sort of mingle with the green object, but they would be prevented because there's no conductor that allows them to flow from blue object to green object. So they just remain stuck. They remain stuck to be negative and then positive on the green one. So the answer is going to be C. Okay, so this is a nice segue into the next sort of idea. Now, big picture here, we're still back in the Greek era, where they used the amber to sort of notice that you can get sparks or shocks, and you can control fur on animals or hair on your head. We haven't really passed the Greek time yet. We will, don't worry, we will very quickly accelerate, but we're just to remind you, this is the story we're still telling ourselves. We're way back in the Greek times. We're still talking about charge. Okay, so we have now admitted what charge is, positives and negatives. What does it mean to have a charged object? Because we've mentioned this a few times now. A positive rod is brought close, blah, blah, blah. What is a positive rod? What does it mean for an object to be positive? Well, we now know, again, this is not known back in ancient times, also not really known back in the early 1900s, but we know that every atom is neutral. It has a mix of, well, neutrons, but protons and electrons, and a neutral atom will have the same number of protons as electrons. By that same logic, a neutral object will have the same number of protons and electrons among all of the sums of all the atoms, right? Because an object is obviously a mix or a collection of either many molecules or many atoms. So a neutral object will just be, if you add up all the protons in the object and you add up all the electrons in the object, they balance. A negative object, well, that just means you have more electrons in the object than you do protons. So overall, you've got more negative charge. And a positive object is obviously the reverse. You have fewer electrons than you do protons, leaving the whole object overall positive. Now, that's fine and dandy. Conceptually, it's fairly easy to get on board with the idea of physically what a charged object is. No problem. Really, the question, though, is how do you obtain something that's charged? You must realize charge is conserved, right? Every atom is neutral. For every proton, there's an accompanying electron, right? You have this sort of conservation of charge. It's nothing new in physics. You've got conservation of energy, it's the same idea. You've got conservation of mass, it's the same idea. You've got conservation of charge, it's the same idea, right? So you have this sort of conservation of charge. So that, if you really think about what the implication of that means is, if you had, magically, a positively charged rod, as we've mentioned previously in a few questions, really your brain should be saying, okay, fine, the answer to that question was easy, but how did we obtain that positive rod? Because if everything in the world is neutral, on average, then if you have a positive rod, then there must be a negative rod somewhere else to balance it out. And that is really what this next slide is about here. How do we create positively or negatively charged objects? There are three main mechanisms by which you can charge an object or transfer charge between objects. So big picture, the notion is we charge objects through means of conservation of charge. If we have we've got two neutral objects, we can borrow some negative charges from one object and put them on another object, and then that creates a positive and a negative object separately. Together, they're still neutral, so you overall are still neutral. That's what I mean by conservation of charge, but that's how you create charged objects. There are three ways in which you can transfer these sort of negative charges to something else. First one is through rubbing or friction. Literally, it seems weird to think that friction, like rubbing your hands together or what have you, yes, it heats up your hands when you rub them together, but it's weird to think about that rubbing objects together and friction can literally scrape off electrons, especially if you understand the introduction of quantum physics, where like electrons aren't particles, they're like waves. So to really think about how friction can pull a wave off of one object into another object is really mind-blowing, but it works. You can transfer objects by friction. So an example of this is when you rub a balloon on your hair. I'm sure at some point in time we've all done this or something similar to this. Or when you get out of the car, you sit up out of your car, and then you go to close your car door and you get a little shock. Same thing. Your clothes were rubbing on the fabric of your seat. That's transferring charge. It's the same idea. So you can transfer charges between objects by physical rubbing. That's one way. This way, the next way I find personally the most interesting. You can induce a charge. Another term for it is called charge separation. The way in which this works is sort of inception, actually, or if you're a math person, it's kind of like induction. But you start with a neutral rod, and the way you can induce a charge in a second object is you can take an object that's known to be positive, say, or negative would also work, known to be charged, I guess, and you bring it within the proximity of the neutral rod. So the neutral rod will experience a charge separation. So in the event this is positive, we see a bunch of positives here, it will attract all the negatives to one end, leaving the other end positive. Now, overall, at the moment, that rod is still neutral. It's just polarized, right? We've separated the charge. Now, how do we obtain a charged object from a polarized object? This is where the beauty and the genius comes in. What we do is we attach a grounding wire from this end down to somewhere else. Could be another object. It could be a grounding wire in a wall socket. There's 3 prongs in a wall socket. The wall socket kind of looks like this, right? That is the ground. It looks like a little face. The little mouth on the face, that's the grounding pin. So you can attach one end to ground, and then that actually allows this side, these charges, to escape. And then what that does is that leaves only the opposite charged particles on the other side. And then if you cut the wire and you remove the grounding wire, then you have trapped the charges on that object. And then you can remove your second object. So that's a way to induce a charge on a second object. If that confused you a little bit, then I'm going to scroll up. It's the same notion of what happened in this multiple choice question here. This happened through induction, right? We had 2 neutral objects. We got a positive object that came close. We had a charge separation. We had all the negatives on this side. We had all the positives on this side. We removed the wire that connected them, and that left this one with negatives and this one with positives, right? That is us creating charged objects through the means of induction, through the means of inducing a charge separation. So that's the second way. There's 3 ways. That's the second way. The third way is through something called conduction. This one's dead simple to understand. Literally through touching. Not rubbing, just touching. So if you have an object that is known to have an excess of positive charges, and you touch a metal object that is neutral, this is neutral because it's got 1, 2, 3 positives and 1, 2, 3 negatives, so it's neutral. If you just touch them, then they will share charges equally. So here, How many charges does this have? 1, 2, 3, 4, 5, 6, 7. 7 positive charges, and this one's neutral. So they're going to want to share the positive charges. So they're going to share it 50-50. Now, 7 doesn't divide by 2 very well. So, you know, one object's going to have 4, one object is going to have 3. I don't really care about that. This is the sort of quantization argument again. In physics, we literally just divide by 2. Fuck it, we just divide by 2. So 1, 2, 3, 1, 2, 3, 4. Yes, I know 4, whatever. We would just say that the charge, let me change my color. The charge on here is going to be half the total charge. The charge on here is going to be half the total charge. That's through conduction. That's through touching. That's how sparks happen. You know, when you touch your metal door, your hand is physically touching the metal door on your car, and because there's conduction there, you transfer the static charge that's built up on your hand. It transfers to your car, and you get a spark because it's completing the circuit. So those are the 3 main methods of charge transfer: friction, rubbing; charge separation, also called induction; and conduction, literally just a simple touch. No friction, no rubbing, just a simple touch. So those are the 3. In the last 3 minutes of the lecture, let's just wrap up the sort of notion of charge transfer, and we will resume lecture tomorrow and talk about introducing the idea of the electric force. That's really where we're building. But I want to finish the story of the ancient Greeks today, and then that way tomorrow we can jump to the 1900s. We can jump from like ancient Greek times all the way to the 1900s in one day. So let's just finish that up before we call it a day. So here's a conceptual, well, sort of conceptual example. It practices conduction. Conduction is the main source of transfer that we're going to be dealing with in this class. So that's why I've chosen to do an example on conduction. So here, this is taken from the typed notes that I've posted online. So the full explanation is typed there for you. So if you're finding it hard to follow or something, you can always go back and look at the typed notes, but let's just do this here briefly. So figure 3 shows 4 panels. This is obviously figure 3 in the typed notes. In panel 1, we've got 2 identical conducting spheres, A and B, and they carry an equal amount of excess charge to begin with. So I don't know what the charge is, but let's just call it Q. Oh yeah, here, Q naught. So the amount of charge on A is the same as the amount of charge on B, and let's just call that Q naught. Panel 2 shows a neutral conducting sphere that briefly comes into contact with sphere A. And then in panel 3, that sphere, that new sphere, is pointed to the other side, and then we touch sphere B with it. And then we throw away sphere C altogether, and we want to know how much charge remains on spheres A and B. Now, in real life, why is this useful? It wouldn't be. This would be a stupid application in real life. This is definitely for teaching related reasons. So if you're trying to think about why this is useful, don't, because it's not. Other than useful in the sense that it helps illustrate a point. So let's just do this step by step. I've already mentioned that, you know, yes, charge is quantized, but we don't really care. We just divide by 2. Like we share charges equally mathematically. We don't worry about plus or minus 1 electron here or there. So I'll show you what that means. We have a neutral sphere that touches sphere A. So I'll say in panel 2, we can say the charge on sphere C is going to be, is going to be the total charge divided by 2, because they share equally. And the charge on sphere A prime meaning after we touch, not before we touch, is going to be the total charge divided by 2. They share charges equally. Now, in this case, what is Q total? Q total is going to be Q naught in this case. So the charge on sphere C after touching is going to be Q naught over 2, and the charge on sphere A after touching is also going to be Q naught over 2. They share charges equally. In panel 3, we now have charge on A is Q naught over 2. We have charge on B is Q naught. And we have charge on C is Q naught over 2. Notice, if you add up all of these charges, you still get 2Q, right? Because that's what we started with, Q plus Q. We started with 2Q. Now we touch sphere C to sphere B. So we are sharing these charges. So what we're doing here is we're saying the total charge that's involved in the transfer is Q naught plus Q naught over 2, which is 3Q naught over 2. That's the total charge involved in this interaction here, okay? That's Q total. So when you touch sphere C and sphere B, when you touch them together, they share charges equally. So QB prime is going to be half of the total charge. Half of the total is going to be 3Q naught over 4. And QC prime is going to be, again, Q total over 2. And Q total is 3Q naught over 2 times 2 is 4. So there you go. So in panel 4, the answer to the question, what was the question again? What are the charges of each sphere in panel 4? Well, A is going to be Q naught over 2. B is going to be 3Q naught over 4. And we've thrown away sphere C. But if sphere C was asked, then we would also say it's 3Q naught over 4. And just to make sure you've done it right as a sort of sanity check, you can add up. Add up Q naught over 2, add up 3Q naught over 4, and add up, if we did have QC still, it would also be 3Q naught over 4. So you'd add up. If you add up all 3 of these, you should equal 2Q naught, because that's what we started with, conservation of charge. So that's an example of conduction for you. That's an example of how physicists ignore the technicalities of math. We don't care really if there's an odd number of electrons. We just kind of ignore that because it's in the 19th decimal place. It doesn't really matter. And we just divide by 2. Okay, so that's what that is. Okay, that's the end of the first lecture. Thanks for sticking around. I know we're kind of 4 minutes over, so I apologize for that. We will see you in the afternoon tomorrow. I think it's 1 p.m. tomorrow, I believe, Eastern Standard Time. So if you're over out west, hopefully you can join us live for that lecture, if that's a reasonable time for you. Unfortunately, I think if you're over in Asia, you might be a 12 or a 13-hour time difference. So that would be 1 a.m. or 2 a.m. for you. You may not be able to join us tomorrow live. That's okay. I will record the lectures and post them on YouTube, and everyone will have the link to that channel later today. So please don't kill yourself waking up at ungodly hours to try to attend live lectures. We will try to make that as accessible as possible for you. But I do encourage you, when possible, it is advantageous for everyone to show up to the live lectures when possible. So thank you for joining us. I'm going to stop the recording now, and I'm going to hang on the line for an extra few minutes, and I'm going to open up the chat window. And I know Romina's probably been diligently answering questions, but I will take some questions as well when I open the chat window. But for now, I'm gonna end the recording. So for those of you who are watching, I will see you in the next video.